Let's talk about molecules and compounds. A molecule basically is two or more atoms of the same elements that are combined chemically. A compound, on the other hand, is two more atoms of different elements combined chemically. A good example of this is if I take hydrogen, I can bind it with another hydrogen, and it is a molecule because it's a molecule of hydrogen. That means it has two hydrogens joined together that makes a molecule. However, if I take hydrogen and join it with an oxygen, let's say for instance specifically two hydrogens joined with one oxygen, then we've created a compound, not just a molecule. It's still a molecule, but it's a compound specifically because it's two differing elements that are joined together. And guess what you got? You have H2O, which is our water. Now if you look right here, you're going to see three different groups or two elements joining together. You have sodium and you have chlorine. When you join sodium and chlorine together, you get sodium chloride. Now it's what we call everyday table salt. That is a compound and a molecule. Why is it a molecule? Well, it's two or more elements joined together. Why is it a compound? Well, they are two different types of elements that are joined together to create something brand new called sodium chloride. Something we like to put on our food. Now, what are chemical reactions? Well, it's easy to say that atoms are united by chemical bonds. Bonds, if you think about bonds in specific ways, bonds are things that tie things together. Like if you bond with someone, you've become close to them, you're tied to them in a way. But atoms, when they bond with each other, they become attached to each other. So that's what a bond is. So atoms unite by chemical bonds. They disassociate from other atoms when those bonds are broken. That means they will separate from each other and go in their separate ways when a bond is broken. Now, energy was required both to create and to disassociate a bond. Now, let's talk about why and how this happens. All bonds are based on electrons. Now, these electrons are going to occupy energy levels called electron shells. They're called shells because they are energy levels on the outside of the nucleus of an atom. Electrons closest to the nucleus are most strongly attracted to that atom. These guys are the ones that are going to be stable. They're not going to be the ones that are going to be shared or shed. Now, each shell has what we call distinct properties. That means they all have their own characteristics. The number of electrons has an upper limit. Shells closest to the nucleus are the ones that are going to fill up first. That means shells or electron pathways that are closest to the nucleus of that atom are going to be the ones that are going to fill up first. Now let's look at this. Bonding is directly involving the interaction between electrons, specifically those that are found on the outermost shell or their outermost energy level of that atom. This shell or this energy level is known as the valence shell. Every time you hear valence, you know it's talking about the outermost energy level of that atom when we're dealing with electrons. Now, when you have a full valence shell, you're not going to have an atom that's going to be very easy to form bonds. As a matter of fact, it probably won't form bonds at all because it's very stable just the way it is. So therefore, it's not going to need change. But you do have atoms that are considered to be inert. Atoms are stable when they're inert, when the outermost shell is complete and full. Now, how do we see if the shell is full or the outermost shell is full on an atom? How do we see basically if that atom is actually very reactive or very stable? Well, the first shell of all atoms can hold up to 2 electrons. Okay? The second one can hold up to 8 electrons. The third shell can hold up to 18 electrons. Now, you have a grand total of upwards to close to, I think, 7 shells that can be filled. Now, atoms will gain, lose, or even share electrons to make sure that their outermost orbitals reach a stable state. That means they have at least 8 electrons in their outermost shell. That's what we're talking about with the rule of 8. Atoms are considered stable when the outermost energy level of that atom has 8 electrons. Now, did we say that the second level or the third level can actually hold up to 18? Yes, but we're not concerned about it reaching 18. We're concerned about, does it get to 8? Now, the exception to this rule of 8s is shell 1. That can only hold 2 electrons. So if there are 2 electrons in the very first energy level, that energy level is going to be stable. There are only a couple of atoms that are going to be dealing with that particular energy level when it comes to bonding. One is hydrogen, the other one is helium. Now let's look at this diagram right here. Now, chemically inert. If you look on your left, over here, you're going to see a helium atom. Like I said, it's going to follow, it's one of the exceptions to the rule. Why? Because it literally has only one energy level. It has one shell. How many electrons does it have? 2. Remember, what we said about the first shell is it's going to have a maximum. That means the most it can ever possibly have is only 2 electrons. And we can see that evident right here. So this helium atom is actually stable. It's not going to bond. It's an inert element. Over here, neon. This is an inert element also. Why? Well, how many does it have here? It has 1, 2, 3, 4, 5, 6, 7, 8 electrons right here. If you look at this, and we call this the electron dot formation also, if you'll remember from earlier, this is a planetary model that we're going by to be able to judge this atom. You're seeing 8 electrons on the outermost shell. Remember the rules of 8. It is a completed outermost shell, and so it's going to be considered stable. Now, both this first shell and only shell and this second shell are considered to be valence shells. Once again, the outermost shell. So from now on, I'm not going to say outermost shell anymore. I'm going to say valence shell to kind of make that hit home. Now, reactive elements. When the valence shells are not full, they are considered to be unstable. Now, how unfull they are determines how unstable they are and how quickly they react. So, they tend to gain, they tend to lose, or they tend to share electrons. This allows for a bond formation, and when this is done, it will produce a stable valence or a valence shell. Look right here. Sorry. Whoops. I'm going to wait for that to stop spinning. Now, if you look at hydrogen, right here in the top left-hand corner, hydrogen has only one shell, just like helium. However, hydrogen only has 1 electron. So is it stable? Is it inert? No. It is not inert, it's not stable because it only has 1 electron in its outermost or its valence shell. So therefore, it's going to need to gain a new electron in order to become stable. Carbon, look at this. It has how many on the outside? 4. If we go by our rules of 8, it has to have 8 to be stable. So it needs 4 more electrons to become completely stable. Oxygen, it has 6 on its outermost shell, so it's going to require 2 more to become stable. And sodium, right here. Sodium is unique in this whole gamut because sodium only has 1 on its outermost shell. So it literally is going to have 7 to become stable. Now, the fact that it only has 1 is going to come in is going to play a role later on in the types of bonds that sodium is going to be able to perform. The same as these others, sodium is going to be unique. It's going to perform a different kind of bond than the other 3 elements. This concludes our 4th video. If you would like to hear more, continue on to the 5th video.